Welcome to CS 340, Machine Learning Data Mining. I'm your host, Frank. This is Payman. We're talking about regularization today. It's fall 2020, and we're at a new low in terms of lecture attendees. Makes me feel awesome to be spending this time lecturing live and not many people are showing up. Maybe I should just stop doing it. Maybe then you'll appreciate it. I don't know. They'll appreciate it. Who knows? Cool. There's some admin to cover. Obviously, there is a midterm that will be released on Monday if everything goes well. It's take-home examination. It consists of a solo endeavor problem, and then you're coming to 1/5. Wow. Okay. So I guess I'm doing a little better than that, but it still, it still hurts. Like that. I want to feel the love. Okay. There'll be a solo endeavor and a Kaggle competition. Hopefully all of you know what Kaggle competitions are. If you don't, look it up online. It's competitive machine learning. Yeah. The Kaggle competition can be done. So it can be done in teams of five. However, you cannot have overlap. No overlap in teams between midterm and final. And I know you can't read that, that's fine, but I just said it, right? Okay, so that's like, think about this, think about your strategy for team selection, right? You probably want to go with a weak and crappy team for the midterm and then a strong team for the final, because you can't have overlap, okay? Or just Lone Ranger it, do it yourself. I don't know, whatever. When is the competition? It is part of the exam. It's the second question in the question. Will it be doable solo? Everything is doable solo. The question is whether or not you can do it in the amount of time. Sorry, what's the solo endeavor? There's one question which you do by yourself, and then there's a Kaggle competition afterwards. Yeah, questions about that. So you can use some time at the end of class to do partner selection, or reach out on Piazza and get your partners selected if you don't know 8 people in the class that you might want to partner with, right? You can work in smaller teams. It is doable. It's just, team of 5 maximally for the midterm, and a non-overlapping team of 5 for the final. If you're the one, then that means you need 8 people to know, right? Do our teams have to be confirmed before release? Are you in prison or something? I don't understand. Are teams mandatory? No, they're not mandatory for the midterm, and no, you don't have to make the team before we release the examination. Make it, what does non-overlapping team mean? Oh my goodness. Hi, Sophia. It means you can't have any of the same people on your team for the midterm and the final. Hopefully that's clear. Okay, shall we get going? This is one of my favorite lectures of the term. Starts to make sense. Okay, we talked about feature selection last time, and talked about choosing relevant features, whatever relevance means. Most common approach is some sort of search and score method. You define a score function, you search for the features with the best score. But we said, and it is true, that it is difficult to define the score. I just figured out actually that I can achieve my step goal without actually taking any steps at all. I just have to wave my arm around enough during the day, apparently, which is pretty cool. That's how I'm getting fat, I guess. So it's hard to define a score, and it's hard to search. Combinatorial problem. So we often use greedy methods like forward selection. That totally works, but they really work on toy data well. They're super frustrating on real data. When you try different feature selection approaches, you're going to get different results, and determining whether a feature is relevant is complicated and ambiguous. So my/our approach advice, if you want to find the relevant variables, try the association approach. It's simple. It's easy. Makes sense. Try forward selection, like we described, with different values of lambda. Try out a couple of other feature selection methods too. then go talk to somebody who knows something about the application domain, right? Like they should have some idea about which variables are relevant and why. And whenever you're talking about variable selection, never be overconfident. Like don't say things that just simply aren't true, right? Like you need to make statements like, the algorithm has found out these variables are helpful in predicting y, and that's basically the only statements that you can make, right? You should make all kinds of warnings that the models are not perfect at finding relevant variables, and certainly these kind of relevance selection methods are not discovering how the world truly works, what the true relationship between input and output is. Case in point, for instance, when you do relevant variable selection, you're going to be subject to survivorship bias. Like the features that you actually care about are prone to be missing, right? So this is I think this is due to Wald at Columbia was asked to do a statistical analysis to figure out where they should put armor plating on planes that returned from battle in World War II. And he was given basically, diagrams of planes and where the bullet holes were. And the analysis was like where, like what features, like which holes are relevant for where to put the armor. So judging from this, which would be the relevant parts of the plane to protect? Payment.
It's the part that has the most dots on it.
Okay, so that's what the Army engineers did. They were like, oh yeah, that's where they're getting shot, so we should totally put plating there. Payman has been tricked. This is true. A weakness in a TA. Yes, of course, the planes that come back are the ones that have actually survived, but obviously a bullet right there is really, really bad, or a bullet right there is really, really bad. And actually the data that you see has this whole massive missing component to it, right? So, actually the relevant parts to protect are the ones where there are no bullets, because those are the planes that don't come back, bullet holes, right? So that's where you need to put armor. And this kind of, this kind of survivorship bias it affects all sorts of stuff, right? It's certainly going to affect, feature selection and that sort of thing, but people come to all kinds of weird and wrong conclusions due to survivor bias all the time. Like there are articles on secrets of success. They always focus on successful people, but they never look at like the non-super successful people with the same traits, right? Same thing with allergies and mental illness and stuff like that. Cool. Okay, awesome. So you may have noticed you may have noticed that Payman, you definitely need to watch the chat channel because there's too much stuff going on for me to watch it right now. So you may have noticed when I've been talking, I have been conflating feature selection and model selection, although I probably should have done a better job of keeping them separate while we're talking about them as individual things. The reason is, of course, that they're kind of the same thing, right? But we've been talking about model selection. I've been trying to use model selection when we talk about which model should I use, KNN versus decision tree, which depth of decision tree, what degree of polynomial basis. And I've tried to use feature selection when I've been talking about which features should I use. Should I use feature 10 or not? Should I put xi squared for some xi as part of the basis that I use, right? Obviously, the reason why I'm screwing up saying feature versus model selection is that the two tasks are really highly related, right? It's a different model if we add xi squared to a linear regression model, right? We put this in the basis. It has a different number of parameters. It's actually a different model, right? But the xi squared term is just a feature that can be selected or not, right? If you have a large set of features, you can turn it off or on, and it's like one of many features. So okay. So I think of model selection and feature selection as basically being the same thing. But usually when people talk about feature selection, they mean choosing from some set of original features, whatever that happens to be. And model selection is the broader endeavor, right? So you can say that feature selection is a special case of model selection. Can it help prediction if we throw features away? Yeah, this is because linear regression can overfit with large D, period, even though it's just a hyperplane, right? And we kind of know this already. If we, choose some feature space that's d-dimensional, that's equal to the number of output observations we have, and we use completely random features, just totally random features, right? with high probability, modulo some collinearity issues and that sort of stuff, basically with almost certainty, almost certainly you'll be able to get away, you will be able to achieve a training error of 0. Obviously, this means that the model is completely overfitting, right? It's just fitting noise, right? So yeah. So obviously, getting rid of features can be helpful if you can get rid of spurious signal, right? And you end up overfitting less. So you can view the number of features as a hyperparameter, and the model gets more complex as you add features. Okay, questions at this point? Cool. All right. So let's think about, and we'll hurry up so we get back on schedule because it was late. So
would the data's validity be problematic if you can?
I don't know what data validity is. Like all we care about is predictive accuracy, and if you get better generalization performance by using fewer features, we win, right? So let's think about polynomial degree. We've thought about that for a little while, and training versus testing, right? And we've made the claim that complicated models tend to overfit more. And what does this what does this mean? And worse, what if we actually need a complicated model, right? Now, why would we need a complicated model, right? The true mapping from some input, whatever the input is, an image to a label, or from the features of a spam, of an email to spam or not, or whatever, that mapping is usually very, very, very complex. It's not clear how many features you need. You might need a very, very complicated mathematical expression to represent the function from input to output. So you might need a very, very high degree polynomial, or you might need to combine many, many features and you don't know which ones are relevant, so on and so forth. But the relationship is complex, right? But we know that complex models overfit, like models with lots of parameters tend to overfit. So what do we do, right? And we have some standard tools. Our main tools for dealing with this are model averaging. We know about this. This is an ensembling technique. We average over multiple models to decrease variance, and regularization, where we penalize what we often call the complexity or expressivity of the model. And what's sort of fun is these two together basically are Bayesian ML methods. And that's 440 and 540 and my grad classes. So, you know, go take those when we want to really do both of them together. Today, we're going to talk about this, okay? But first, another quiz question for Payman, see if he's paying attention. Let's see if he gets this one right or not. It's a tricky one too, actually. So let's look at the following data set and look at 3 regression models. So there's this blue model, then there's a red model and a green model. So which regression model would you prefer?
I would choose the green one.
You would choose the green one. Well, that's silly because the blue one is awesome, right? So I'd choose the blue one out of this. But if you had to choose between the red one and the green one, stop clicking ahead in the slides too, if that's what you're doing. If you're forced to choose between the red and green, not both are wrong. I'm forcing you to choose, right? And they have the same training error, okay? So they're indistinguishable from training error. Which one would you prefer?
I guess slope of the green one is less, so it's less sensitive.
Okay, so, well, okay, so so Payman is right. You should pick green, but the question is why, right? So like Ockham is writing, is it better to approximate than over approximate? I don't know what that means in this particular case, right? But, and this will become clear in just a little bit, right? And actually, this is one of the more important slides to kind of internalize somehow, although you won't really understand it until several years from now, and you'll come back and you say, oh, I know what's going on here, but I'll try to make it clear in another slide, right? Since the slope is smaller, small changes in X, right? If we move along in X space just a very, very little bit, like make small changes in the prediction, right? So that means that, like, you can argue that the green line's predictions are less sensitive to having W exactly right, because like it's going to make small changes, right? Out here, if you make, in red, if you make a small change in X, right, you're going to make a very, very large change in the prediction, right? So you're very, very sensitive to the value of W, right? Cool. So you might think, and this will be clear, I think, more in the polynomial case that we'll talk about just in a little bit, since the green line is less sensitive, it varies its prediction less for small changes in input, it might lead to lower test error. Okay, so let's think about what's going on here. I should have fixed this between, but I've been working on other things. So whatever this means, right? We'll get to it in just a second, right? So basically, in order to make a 7th degree or the 7th order polynomial wiggle enough to fit the data exactly, you need to actually put very, very large numbers as the coefficients on those polynomial orders, okay? However, if you make the parameters small, right, that even a 7th order polynomial will wiggle less. So let me explain what I mean, right? So there's lots of ways of thinking about this, right? So this is the kind of thing that happens when you fit a model like this. You get very, very large numbers here, okay? You could, and we're going to talk about how to do this, you could fit a 7th order polynomial in such a way that the numbers are small. But you'll notice that this actually looks more or less like a constant model with just a little bit of a cubic term and so on and so forth. So this looks more like a cubic function than it does a 7th order function because it's really, really small. More to the point, when you move X a little bit here, just a teeny tiny little bit away from a data point, right, like here, right, because the numbers are so huge, the prediction changes a lot, dramatically, very quickly, right? So it's saying that, like, in the space of input-output things, just a small change in X makes a really, really big change in the prediction. Whereas over here, because all of the parameter values are smaller, you make a small change in X, the change in the output is much, much smaller, right? Okay. So that intuition is really, really important and is basically the over here. So like I said here, right? So if we have an X value here and we make a very small change in X value, the change in Y value from here to there is very, very large, right? Okay, yeah, good. Whereas clearly, if you have a 7th order polynomial that looks like this, the change from a small wiggle of X is going to be much smaller by virtue of the fact that these weights, the parameters of the regression model, are actually smaller in value, right? Cool. So this gives rise to the most common regularization strategy in machine learning, and it's one that I hope I will convince you today that you should basically just always use, right? So the standard regularization is L2 regularization. So here's our standard, sum squares loss for a regression model, right? Think X, think Z, doesn't really matter, same thing. What we're going to do is we're going to we want to minimize this, right? So we're going to add something else that we want to minimize just as much, right? And we want to minimize as well the size of the individual parameter values, okay? And we can write this in our matrix notation, noting that this we already know how to do, and this is just the squared 2 norm of W. Okay, so we just want to like make the W vector small, basically. Right? So the intuition is that large slopes, we could say parameter values here, right? When we think back to the regression example that we just saw, tend to lead to overfitting, which is to say, what do we mean by overfitting? It means doesn't generalize well to test data, right? It's going to overfit to specific particularities of the data and doesn't generalize particularly well. So this objective here balances between getting very low error, right? We want to minimize the error, but we also want the polynomial regression or the regression parameters values to be small, right? And the net effect is that basically we're saying to our fitting procedure, our learner or whatever, when we're like fitting the model, that you can increase the training error actually a little bit if it makes the values of your parameters a little bit smaller, right? And the nice thing is this almost always reduces overfitting. And of course, this has a standard, regularization parameter lambda, which has to be greater than 0, and it controls the strength of the regularization. If you put a large lambda on here, it puts a very, very large penalty on the value of the parameters, right? Okay. So how should you choose lambda? There's some complicated theory that says basically as n grows, lambda should be in the range from some constant to something that's of order root n. In reality, people optimize a validation set or cross-validation error. That's how you.
What are the disadvantages if the prediction is sensitive to X?
So, okay, good question. Look again here, right? So I don't know what the actual function is that interpolates this data. Is that the actual function? Is this the actual function? Whatever, right? But I expect that when I'm close to data, right, in a regression setting, right, what I expect when I'm close to data, that my output value is also close, right? Nature is not evil, right? If I weigh, half a pound more, my IQ isn't going to go down by 50 points, right? It's like, it just doesn't work that way, right? So if you have, a prediction that's very, very sensitive to X, that means that the output is going to change a huge amount when you change X by a very small amount, right? And that is generally something that when the relationship is smooth and data actually comes from natural sources, doesn't happen very often, right? Okay, no, I may never be able to, okay, good. Hopefully that makes sense. Okay. So technically speaking, our model could be 7th degree polynomial because of the weights in W, the 7th degree polynomial. The 7th degree or the 6th degree or the 5th degree won't have a lot of impact. That's exactly right. Okay, that's exactly right. And you can start to see where what we're going to eventually get to is this model selection or this feature selection mumbo jumbo is just going to get thrown out the window because we're going to be able to regularize our models to deal with a very, very large number of features, even if they're irrelevant. And that's actually that's where machine learning sort of kicks in and like takes over. It's like, just throw a boatload of features at something and regularize and Bob's your uncle in UK speak, which never made sense to me. That means everything's going to be fine. Or you're set. So let's look at what's going on here, right? So this is an L2 regularization shrinking example where we're going to shrink the parameters values, right? So here's the regularization strength. Greater value of the regularization parameter lambda means more shrinkage, right? This is a 5 feature regression problem. So we've got 5 parameters, W1 to W5. Here's the 2 norm of the residual, right, of this residual vector. And here's the 2 norm of the parameter vector, right? Okay, so as lambda gets larger, you expect the 2 norm of the parameter vector to get smaller. In other words, the individual weights, the values of the parameters are going to get smaller. So the sum of the squares of those is going to get smaller, starting at something around 16, goes down, right? As you increase the amount of regularization, you expect your training error to go up, right? Because you're forcing the value of the parameters to be away from optimal, right? So that's what happens here. The training error actually goes up, right? And more to the point, you expect that the values of the parameters are going to move around, okay? And they may move around in interesting ways. So as you add regularization, the absolute magnitude of W5 here actually goes up in absolute magnitude, right? For a little while, you see, right? Most of them go down, but some can even go up. Okay? And what you can see here, so like just to restate this, right? What we want is we want to tolerate some amount of slippage in the loss sense, right? So if you notice, these losses are all kind of the same approximate value, right? But the norm of the weight vector is significantly smaller at a lambda value of 64 here. Right?
Would this imply W5 is more important feature?
No, not necessarily. Again, what is important, what's relevant, this is a complicated thing, right? Maybe. Well, maybe. What's the difference between doing this and just using a smaller degree of polynomial? Well, again, what if the relationship it requires a complex model, right? You actually have to have a complex model. You just want the complex model to be well behaved. That was kind of the setup for this. And that's really what we're going to have. Like, how do you predict that a message, an email is spam? It's crazy to go from some feature space to that. The functional relationship, if you think about what the actual functional relationship is, that's some crazy thing. I have no idea what it is, right? So you need, for instance, as we see here, in the chat, you may need a very complex polynomial, right? Or in general, a very complex function, right? In these linear models, that means some set of basis functions and so on and so forth, right? If you need that, then you need to be able to fit it in a way that actually makes the model well behaved, even though you have a very expressive complex model. So a nice plot that you'll see, and it took me like longer than I care to admit to understand what these plots were, but they're kind of cool. These are regularization path plots. And I don't mean recently, I mean when I was a grad student, right? So the regularization path is a plot of optimal weights as the amount of regularization varies, okay? So what you have here on the vertical axis are the parameters of a regression model. I don't know how many parameters there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, something like that. 13 different parameters. So this is like a D equals, is approximately equal 13 here. Okay. And for a very large number of regularization parameter values, lambda, right? You fit a very large number of them in order to make this curve smooth. In fact, you can see all of them. There's one, there's all the kinks in the curve. So there's a bunch of them, right? You fit the model, and what we're plotting here are the actual parameter values, the weights applied to those features as a function of regularization strength. Okay. So the comment, it's W coefficient, it's a number. Yeah, exactly. So the comment before, some people do features. By the way, there's a huge amount of computation here because you have to solve like 1,000 different linear regression models, all regularized by a different amount, right? But some people use this for feature selection. They go in and they say, okay, well, which of the features have survived at, up to some, like which are the most important or relevant features? They're the ones that take the longest to go away when you regularize the model. So this is an important / relevant feature. This is too, but maybe these ones are really not, right? So it's related to what we were talking about before. Starts with lambda equals 0, and all the weights obviously converge to 0 as lambda grows. If you make lambda infinity, then the only thing that matters is the norm of the weight vector, and in order to minimize that quantity, you just set all the weights to 0. The nice thing is that this regularization plays very well with everything that we've done so far, right? So when using L2 regularized squared error and the linear regression losses we've looked at, you can actually solve in the same way that we did with the normal equations. You can solve the equation that arises from setting the gradient function equal to 0. So our least squares loss was this. After we add regularization, we just add the norm of the parameter vector squared. There's 2 norms squared. If you take the gradient, we know from before that the gradient of the initial expression looks like this. And if you just look right here again, the gradient of that is pretty clearly this. So the gradient after adding regularization looks like that, right? Which means that we can construct our linear system like we did before, and with regularization, and the only thing that happens is this lambda shows up here times the identity matrix. Okay. All right. Cool. So now we have a linear system with regularization. Awesome. Okay. What's even more awesome is, unlike X transpose X, because you're adding a little bit of value in every row column pair, basically along the diagonal, now you know that the rank of X transpose X plus lambda I is full rank. It's D rank. Its rank is D. So it's always invertible, which means that you can actually solve the least squares problem by taking a matrix inverse. So you can actually solve this without doing, Gaussian elimination. You can just solve it by inverting the matrix, okay? And it will always be invertible unless lambda is 0, or you have numerical errors when lambda is super, super, super small, potentially. We can also do gradient descent. Doesn't change anything, right? So gradient descent, we said, okay, let's take our regular expression, add the regularizer. We just derived the gradient expression for the regularized least squares loss, right? There's a gradient. So we had our gradient descent iterations from before. This is what we had before. This is the gradient expression. We move against it, right? When we add regularization, the gradient expression is just different. So before regularized, before regularized, before, am I annoying you yet? Regularized, right? Okay. And the cost of gradient descent per iteration is still the same. What's really not obvious, but you can actually show that the number of iterations of gradient descent that you need to reach convergence decreases as lambda increases. You can sort of think of what this is doing is adding more convexity to the problem. It's making another bowl that makes it quicker to go down to the global minimum. So why use L2 regularization, right? It's a weird thing to do, but we CS340 professors say always use regularization, right? The statement that we made before about it almost always decreasing test error should be enough to convince you, right? Like that's what we want to do. We want good test error. So you should, if we say that it's going to give you better test error, you should probably do it, right? But there are a bunch of more reasons. One, the solution W is still unique in the linear regression case, right? X transpose X need not be invertible. There are no collinearity issues, right? It's less sensitive in the sense we talked about to changes in X or Y, right? Gradient descent converges faster. Bigger lambda means fewer iterations. And there's a beautiful result called referred to as Stein's paradox, which is when the dimension of your parameter space is greater than 3, shrinking in the way we're talking about moves you closer to the true parameter vector, period. And in the worst case, you can just set lambda to be something small and you get the same performance. Okay, questions? Do we still arrive at the optimum point with lambda? Could lambda make us go over the point? I don't know exactly what that means, but there still is a global minimum, and it is the global minimum of the regularized problem. So there's no downside to regularization. There is a downside to regularization. You can select a regularization, an amount of regularization that is too large, and then you degrade your performance, period. Right. So there can, just like everything in life, moderation takes the day, right? So you want to just, yeah. So should we cross-validate lambda and the basis separately? So nice, Declan. So again here, you can do whatever you want, really, but what we're trying to establish here is that you don't actually have to change, like you just make a whole bunch of features, make as many as you want, right? And the regularization strength should save the day, right? But that's not entirely true. You have too many features, then you've got, you've got issues. We'll deal with that next lecture. But we CS researchers always use regulations as one of those undergrad lies. You better give better methods. You give better methods and more in-depth discussions. No, actually, this is pretty much not a lie. It's not like Newtonian physics is all wrong. That's the most horrible lie that I think we all experience in our lives, right? Yeah, regularization pretty much just works. There are different forms of regularization that you use in deep neural networks that this is called weight decay in neural networks, and people sometimes say that it works or it doesn't work and so on and so forth. But in general, it's a good idea. So this applies to functions beyond polynomials. Yes, it does. More to the point, you should really think about this is just like the function that you're actually computing. Remember, like when you expand the basis set and you add all sorts of different stuff, the input-output function is very, very complicated, right? It can be very, very, very complicated, particularly if you start adding cross terms, right? Like the function can be effectively arbitrarily complicated. So you really are thinking about regularizing the parameters of whatever functional relationship. Can you explain more about why gradient converges faster? Not in this course, take 540. Okay, thank you. Gradients become larger. It's more about the convexity, right? That's good. All right. So we have to talk about feature regularization or feature standardization here just a little bit, because it's a little bit different when we do regularization. So we talked about this, so we can go quickly through it, right? Let's think about continuous features with different scales. Allergy example: pasta in cups, fish in grams, milk in gallons for me, egg in units of eggs, right? Should we convert these to some standard unit, right? And we already know that it doesn't matter for decision trees or naive Bayes, because we only look at one feature at a time, and the rules are set up that, whatever, you just look at the values in whatever units they're in. And it doesn't matter actually for least squares, because basically you can say that, WJ times 100 milliliters gives the same model as WJ times 0.1 liters, where the units are different, and that means that the weights can be different. Okay, cool. It does matter for k nearest neighbors. We talked about this, right? Because the distance that you compute will be affected by large feature values more than small feature values. And it does matter for regularized least squares, because if you're penalizing WJ squared, it means a different thing if the features are on different scales, right? Cool. So it's common to standardize continuous features. We already talked about how to do this, right? By replacing whatever feature in X or Z with its Z score, by computing the mean of the feature and the standard deviation of the feature, and then replacing the feature with the feature value minus its mean divided by the standard deviation, right? Now changes in WJ will have similar effect for any feature J. In other words, the regularization strength, when you square them, will look basically the same. How do we standardize test data? Obviously, let's not be dumb about this, right? When you estimate these things now become part of your model, part of the program, right? Which means you don't want to compute the mean and standard deviation of the test data and then z-score your test data. What you want is to use what you want to do is use the mean and standard deviation of the training data, because of course, obviously, the test data and training data mean and standard deviation could be very, very different, right? And when you do feature standardization and you're doing cross-validation, if you're doing tenfold cross-validation, you compute the means and variances on the on the training folds, however many of those are, 9 here, and then you standardize the remaining fold with that training mu and mean and standard deviation, and you standardize for different folds, right? Okay. In regression, we also sometimes standardize the targets, right? And then this puts the targets on the same standard scale as the standardized features, right? So you z-score the target, right? What's nice about this is that when you standardize the target, if you set that all of the weights equal to 0, right? The prediction that you would make once you un-z-score the prediction is exactly the average value, right? So it like stabilizes learning somehow. And this shows up in deep neural networks in terms of batch norms and stuff like that, right? So in fact, actually, the really good thing here is that when you add a lot of regularization, then this basically encourages you to predict something closer to the average value of the outputs, which is generally a good idea, right? And the same thing applies, standardize the test data with the training stats, right? And you can do other transformations to the output, logarithm, exponent, and so on and so forth. And these make sense for different kinds of processes like geometric or exponential processes. Should we regularize the y-intercept? This is a reasonable question, right? There's like, you could argue in both ways. No, we should encourage it to be closer to 0. It could be anywhere, right? You should, the argument would be that you should be allowed to shift the function up and down globally. Yes, right? It makes the solution unique and easier to compute W, like we've just talked about. The compromise that lots of people use is to regularize the intercept with a smaller amount than the other variables. So we actually separate the intercept term off of the rest of the regression parameters, right? W0 is here, XW is here, right? You use regularization of the normal kind with a normal strength on W, and you use a different regularization strength on the intercept. That's something that you can do to get better performance and sort of regularize the intercept in an acceptable way. Okay, we're gonna power on. Get through this. I started a little bit late. Something you might end up doing on the midterm is predicting the future. That's okay. The way you're going to do it is a little bit more it'll be okay. You'll see. But it's worth thinking about a couple of things when we think about predicting the future. In principle, you can use any features X that we think are relevant, and this means that it's tempting to use time as a feature and predict the future. As a feature, predict the future. So this is the men's world record for the men's mile. This is the year. This is some non-linear relationship learned by linear regression, right? What we need to be aware of is that we should be cautious about this, right? So 2017. Here's our data point, right? Fine. Maybe even more obviously, here's the male 100-meter sprint time. So here's seconds, years since 1912, right? Which of these is right, the gray or the red line? Payman?
I guess the red one.
Yeah, it seems like a reasonable thing, but you know what? Usain Bolt just screwed everybody up. Okay, so maybe we don't know, right? That's the whole point. And this, we've talked about this, so I don't have to go into it in much detail. Interpolation is a task of predicting between or arguably near data points. Regression models are good at this if you have enough data and the function is continuous. Extrapolation predicts outside the range of the data points. And without assumptions, regression models can be really, really bad at doing this, right? In the model we just looked at for the regression, for the 100-meter times, right? And if you run them backwards in time, it predicts that humans used to be really, really, really slow, like me today. And if you run it forward in time, they might predict arbitrarily small 100-meter times. Or if you just do the linear regression curve that actually explains the Usain Bolt data better, you would predict negative times in the future, right? So you'd like race and in the race before you actually started, which would be pretty cool to watch, actually. So we talked about the no free lunch theorem, consistency, future, so on and so forth, but let's just look at some examples to drive this home, right? if we have some time here, we have the first available measurement and the present, and this is our data set, right? Least squares looks like it might be a reasonable fit, but it could be that there's actually, you know, some other model that fits the data well, and it might actually be better, but it's more complex, which means in this particular case, the training error might be a poor approximation of the test error. Occam's razor says you should take the simplest model every time, right? That's basically what it is. Among competing hypotheses, take the one with the fewest assumptions. The fundamental trade-off formalizes this, suggests that we should suggest the linear model, but the no free lunch theorem kicks in here, which is to say that there exist possible data sets that you should mean that you should select the green model. You can resolve this by collecting more data, right? So if you collect the red data, then the green model looks much better, right? The new data agrees with the green model, it's more plausible, but there's still no free lunch, right? You can collect even more data, right? Now the green model is not a good fit, right? And the idea is that there's some consistency zone, like universally consistent methods converge to the best model here as the data goes to infinity. But when you start talking about extrapolation, now you're in the generalization error zone, which is over here too, right? We don't get data from the future. We don't know what's going to happen, right? And without making strong assumptions, the data from the present really actually says nothing about the future, right? And this is, I'm not going to turn, climate change is real. We're not going to turn all right wing here, right? Has the Earth warmed up over the last 100 years? We're in the consistency zone. The data clearly says yes, absolutely. There's no question the data says yes. But will the Earth continue to warm over the next 100 years? What's the shape of that going to be? Well, this is now subject to generalization error extrapolation, right? We should be a little bit more skeptical about models that predict future events. So should we all be skeptics like, right-wing US Republican people? Right? No, probably not. Among other things, if we average over models that overfit in independent ways, like our ensembling methods, we expect the test error to be lower, so this gives us more confidence. So we should be skeptical of individual models, but agreeing predictions made by models with different data and assumptions are more likely to be true. And data that's near in the extrapolating sense to the current time are likely to be pretty accurate anyway. And again, you can make some smoothness assumptions, and nature kind of is smooth. That's one of the most common assumptions that you make. It's probably reasonable to assume that there's no big jumps that are going to happen. Variance is higher in the future, so the predictions are less reliable. You're relying more on assumptions out here and less on the data. Index funds, you can think about, like, we want to do extrapolation when investing money. What will this be worth in the future? And you can think of index funds as an ensemble method for investing. Like, you buy a stock in the top 500 companies proportional to value, and this tries to follow the average price decrease, right? This usually outperforms most fund managers. Okay, so in summary, we talked about regularization, really, really important, right? It's basically adding an explicit penalty on model complexity. L2 regularization is like bog standard. You need to know it. It's penalty on the L2 norm of the regression weights, and it almost always improves test error. Use it. Standardizing features, it makes sense to put your features on the same scale, particularly if you're going to do regularization and for some model classes. And we just went through very quickly things that you should sort of understand, which is the difference between interpolation and extrapolation, particularly in regression models. And the real idea that we want to convey here is that machine learning models with large N are often very good at predicting between or near the data, but without assumptions, they can be really, really bad away from the data, basically. And that's it for today. I think next time we'll go for even more features. Thank you very much for your time. Questions?
When doing regression with sinusoids, how do you choose the frequency?
There are several ways that one might do this. You can choose a basis that has lots of different frequencies in it and just add more and more frequencies as different functions in the basis. Alan is hinting at the deep learning approach, which is that you can indeed, in that particular case, include the frequency as part of the loss and explicitly make it a parameter that you use gradient descent to learn. Yeah. For the Kaggle competition, can we use sklearn models? No. Not that I, no. Yeah. Why can't we use the mean and standard deviation of the test data when standardizing features? Well, you can, but it wouldn't work very well. Because with very high probability that I mean, just to do this, you get one test data point. What are you going to do? Right? You have to standardize it in some way, and that should be part of your model, right? The more sophisticated way of looking at it is even if you get a batch of test data points simultaneously, when you predict them all, the mean and standard deviation that you would compute on that test data would be very different than what you'd compute on the training data, and which means that you'd be actually putting stuff in that is, in fact, not near the data. So you'd be sort of extrapolating, and that would be bad. Can we use code from the assignments? Yes, that's the idea. Can we upload our model in a pickle format? You don't have to upload your model. You'll have to be putting it in your LaTeX document just like usual. Is the midterm info on Piazza? The midterm info will be on the midterm when we release it. Is there a restriction to what kinds of models we can use? Yes, in the midterm, there will be the first part will tell you exactly what models to implement, and there will be new creative and interesting models to implement that you'll love us for having you think about. And for the second part, you will be using linear models, period, because that's what you've learned. But you can do all kinds of feature engineering, which is where the fun's going to be. For the Kaggle, you will only be able to use linear models. Yeah, that's correct. Yeah. And that means you have lots of code for it. I'm not trying to be super evil, just a little bit evil. Your models will not be evaluated by hand. Your code will be evaluated by hand, but the model will be evaluated automatically. Dominic, I hope it doesn't take a huge amount of time either, but I hope that it gives a good signal as to how everybody's doing. Can we use different loss functions? It's a good question. Yeah, I don't see why not. You have to think about what an ensemble. Yeah, okay, yeah, you could probably do that too. I don't. We could. Probably not going to nail you to the cross for that. That's a good. That linear regression tree is probably out, but yeah. We'll have to think about whether to restrict that. Yeah. No, that's all good. I like the creativity. Okay. Anything else? Otherwise. Oh man, why can't we regularize least squares when converting to standard? We can. That's the whole point. Like you can regularize anytime, but the meaning of the regularization and the strength of the regularization will be different depending on the scale of the feature, because the scale of the weight applied to that feature will be dependent on the scale of the feature. So, and when you're taking the square, large parameter values are going to get impacted more, and you might need a large parameter value, period, to deal with a feature value, which is large. All right, everyone. That was lovely. Thank you, Raymond.
Thank you. Have a nice weekend.
You too. Cheers.